Welcome to ELEC142 Semester 2, Problem Sheet 3 Solutions Part 1. So this is a short problem sheet. This has only 3 questions, but I'm going to record it in 3 separate parts so you can choose the one that's relevant to you. These questions are all circuit-based questions and they're very similar to the sort of thing you're likely to see in an exam paper, and they all tend to be variations on a theme of things we've looked at in the lecture. So you remember this part from the lecture slides where we've already looked at how we solve simple circuit problems where we have just 1 or 2 circuit components. What we're looking at now is what happens when we have complex impedances in series and also in parallel. When I say complex impedance, previously I've used the term reactance. Reactance technically is independent of phase. It's the magnitude of the peak resistance. What we do is we call it the complex impedance and we give it the symbol Z when it's a complex number. So we have some magnitude and some phase in polar form, or in rectangular form we have a real part and an imaginary part. So I've tend to use these a little bit interchangeably, but I'm going to try to move to use the symbol Z, which is the symbol for impedance. And it also has the symbol ohms. So they're very similar measures, and at this point it doesn't really matter what you're calling it, providing you're very aware of what you're doing. So what have we got? So question 1 says, for the circuit shown in figure 1, find an expression for the current I of t and the voltages across the components. So here's figure 1. This is just a hand-drawn version, as you can see, but you can, again, like I said before, it's up to you if you want to draw these out in when you're solving a question, so then you can draw over it, or if you want to sketch on the example sheet, or if you don't even need to sketch at all. It's up to you how you answer it. You're going to get the same answer out anyway. It's just what you find easier to aid your understanding. So we're given that Vn of t is 20 cos 10 to the 3 t volts, and we've got a resistor of 30 ohms and an inductor of 25 millihenries in series. So we've done a problem very similar to this in the lecture, so we've got a worked example there. So what we're going to do is we're going to find the phasor values of the components and also an expression for the current. So Vn of t, I've just written out what our expression is in the time domain. That's just taken from up here. We're going to convert this into phasor form, and we get capital V now is equal to a magnitude of 20 at an angle of 0 degrees. We can do this, we can make this straight conversion because it's a positive cosine, so we don't need to do anything with it. We can see it's 0 degrees because there is no additional phase term here. And we want to write an expression. We know that I of t is going to be a sinusoid because the voltage is a sinusoidal form. So we can write I of t is going to be equal to some peak magnitude cosine 10 to the 3t plus some phase angle. We don't know what that is yet, and we also don't know what the magnitude is yet. But we can assume that the omega t term is going to be the same because it's fed from this voltage source here. So that's your first thing to do in solving these kinds of problems. Convert your voltage to a phasor form and write an expression for the current you're trying to find. Next up, we're going to convert our resistor and our inductor into phasor form. So we're interested in the reactance or the complex impedance of these components. So the reactance of R, or the complex impedance of R, is very simple. It's just the same. It's still 30 ohms. There's no phase component because this component will be in phase with the current flowing through it. The voltage across it will be in phase with the current flowing through it, so there's no imaginary part. The complex impedance, or the reactance of our inductor, X of L, is equal to J omega L, where J represents our phase term and omega L is our frequency and the magnitude. Just put these values in. So omega is 10 to the 3, which we got from here, multiplied by the magnitude of the inductance, that's 25 millihenries. When we solve that, we get it's equal to J 25 ohms. So that means it's a resistance of 25 ohms along the positive imaginary axis. So that's what we've done there. So we've got basically the resistances, or to use the more correct term, the impedances of these two components, these two circuit components, the resistor and the inductor. Next up, we're going to find the voltage. We know from looking at our circuit, and also according to our voltage conservation laws, that the resistance across the reactor, the voltage across the resistor and the voltage across the inductor will equal the total supply voltage. So that's what we've written here. V is equal to VR plus VL. So what have we done here? We've written it out. We know that V is equal to IR, or more correctly, in complex form, it's equal to the current times the reactance, or the complex impedance. So that's what we've done here. We've substituted our resistor value here, and that's going to be multiplied by the current in phasor form, so it's a capital I. And then we've got the same current here. So this is the current, the same current that's flowing through our inductor. And then we've substituted the resistance of our inductor, the complex impedance, into here. So it's just V equals IR, quite simply, but it's in a complex form. So what have we done? We know the value for V in phasor form, so we've just put that in. That was found from up here. And then we've just factorised this, rearranged it, so we've got I outside our bracket and 30 plus J25 inside our bracket. Now we're going to rearrange in terms of I, so we can find an expression for the current. That's what we've just done here. So I is going to be equal to 20 at an angle of 0 degrees over 30 plus J25. Now, as we've done before, we're going to convert our denominator into phasor form to divide it. So that's what we've done here. We've just put it into the calculator, and 30 plus J25 becomes 39.1 at an angle of 39.8 degrees. So once that's done, we can just divide it. So what we do to find the magnitude, it's 20 divided by 39.1, which is 0.51. To find the angle, we look at the angle terms, and it's just 0 minus 39.8, because you subtract the bottom angle from the top angle for phasor division. So that gives us a current of I is equal to 0.51 at an angle of minus 39.8 degrees in amps. So, however, we were asked for this in the form of I of t. So that's what we're going to do. We're just going to do this conversion. So the magnitudes become the magnitudes just transferred down. We know that it's a cosine because that's our convention. We're using phasors. We know what omega t was because we were given that at the start. We assume it's the same as the voltage, and then we just put the phase angle in here. So that's what our minus theta was, and that's in amps. So that's the first part of the question solved. We found an expression for the current I of t. Now we're going to find the voltages across the components, which we've pretty much done almost all the work for. We had this expression here. We said we know VR is equal to I of R. It's just Ohm's law. So what we're going to do is we're going to put our new expression that we found for our current into the equation. So this expression in phasor form, which we found here, we're going to put in. Because we're interested in the multiplication, we're going to use our phasor form. So our current multiplied by the phasor form of our complex resistance. This is quite a simple one. It's 30 ohms. There's no imaginary part, so it's a magnitude of 30 at an angle of 0. If we just do that phasor multiplication, it's 0.51 times 30 for the magnitude. That gives us a total magnitude of 15.3. For the angle, we do this angle plus the second angle. So the angle remains minus 39.8 degrees in volts. So that's the expression for the voltage across the resistor. And we can see that this angle is in phase with our expression for our current. The current angle was minus 39.8 as well, which is good because when we've been discussing this, we've always said that in a resistor, the voltage will be in phase with the current flowing through it. So we've confirmed it. That's a good double check just to make sure our answer makes sense. So the final part, we're going to calculate the voltage across our inductor. So we're using the same principle. The voltage across the inductor is equal to the current flowing through it multiplied by the complex impedance, which in this time we've used the reactance. So we put the value for our current in here, which we had earlier, and this time it's multiplied by our reactance of our inductor in phasor form. So this was 25 at an angle of 90 degrees. You can just convert this because we had it in, what form did we calculate it in? We had it up here in rectangular form. You can think about it quite simply because it's just J, so it's magnitude of 25 along the positive imaginary axis, or you can put 0 plus 25 J into your calculator and do the conversion that way. It doesn't matter which way you do it. So we're just going to perform this phasor multiplication. So we've got 0.51 times 25, which gives us a magnitude of 12.75. And for the angles, we have minus 39.8 plus 90 degrees. And that gives us an angle of 50.2 degrees. So the final answer for our voltage across the inductor is a magnitude of 12.75 at an angle of 50.2 volts.